Salutations, mini mathematicians! Let's keep going with Module 8 and get into our next type of transformation, rotations. You're going to need either some parchment paper or some wax paper today. My parchment paper isn't great for this because it has like grids on it and words to help you like cut it perfectly. So we're not going to use that. I'm going to be using wax paper. If you are someone who can use these little serrated parts, go ahead and do that. I'm going to use some scissors. And then I'm just going to cut a piece. And I'm going to cut just a square-ish piece. So it's about the size of my palm. And this is just so we'll be able to see through. We're going to use it like tracing paper. So anything you can use like tracing paper, wax paper, since one side's a little waxy, sometimes it's a little bit tough. If you're using like a pen, that's going to come off on you, but it's fine. Just wash your hands when you're done, right? Okay, so 8.1b, like I said, is on rotations. We're going to be performing rotations that are multiples of 90 degrees, 180 degrees, 270 degrees, 360 degrees, 360, clockwise or counterclockwise. And we're going to see patterns to write and apply coordinate rules. So x, y is going to go to something all the time, depending on which degree and which direction we are rotating for each one of these types of rotations. Awesome. So let's get our printout. Move these scissors out of my way. 8.1b, rotations. So on the grid below, triangle ABC has been rotated with the center of rotation at the origin O. This process was repeated several times to create the images shown. And just to prove that, if I took my shape, sometimes a marker does a better job with this showing up for me on my dock camera. Something that's important when we're tracing and using our tracing paper is you're always going to want to notice where your origin is, where your center of rotation is. And that way we'll be able to keep the center there as we rotate around. So if I made my center there, and then I traced triangle ABC, sometimes pencils show up on this a little bit better too. Or, ooh, if you had a Sharpie, that would probably work really well. Okay, so I have triangle ABC, and you'll notice if I rotate, I end up being exactly congruent to each one of these triangles. Ooh, how many triangles were there? Could I figure out what degree I'm rotating? So what we want to do now is using tracing paper. So I just did that. I traced triangle ABC and the XY axis. And really you just need to make a little cross. You don't have to trace the entire XY axis. It's just so you can keep your center of rotation there. Pencil works really well, or sometimes I find my finger doesn't work as well because it slides around. So holding our pencil as an anchor on the origin, we rotate the triangle counterclockwise to see if the images were created. So this is clockwise, and we went counterclockwise. You can see if I don't hold the pencil there, they don't line up like perfectly because notice I drifted from my origin. So I'd have to go back a little bit. So just be as accurate as you can. So that's how all these images were created from our pre-image. So So this was our pre-image. So what we want to do is label the corresponding vertices to angle C on all the images of triangle ABC. So what are all the corresponding vertices going to be? They're going to be C prime. So notice, and if you wanted to visually see this again, we could rotate. Oh, there's C prime. Oh, here's C prime. Notice the inner vertex is always going to stay C prime. And it says sketch a concentric circle to connect all the corresponding vertices to angle C. Concentric circles have a common center point. So by definition of a circle, so here's like a circle. The way this circle is created is it's the set of points all equidistant from the center point. So I could use this and draw a perfect circle. I know you don't have one, so I'm not going to cheat. I'm going to use the same tools as you and just connect all these vertices. You're going to be like, wow, I've never drawn a better circle in my life. Yay! So taking a look here, so concentric circles have a common center point, and the center point here is the origin. So all these vertices are equidistant from the center. That's what it means to make a circle. So describe the relationship between angle C and its images to the center of rotation O. So what is the relationship from C to O, or any of these C primes to O? Does this relationship to the center of rotation hold true for the corresponding vertices to A and corresponding vertices to B? So we're going to write out what is going on here. Before we do that, let's take a look, and since this is B, this will end up being B prime. So if I took, let's see, that kind of lines up pretty well. If I took this and drew my really nice circle, it should be intersecting pretty much. Could probably have done that a little bit better. So all the B's are going to intersect. And if I did that again with A, all my A and A prime are also going to intersect. And that's because we have this center of rotation. So what can we say? This is going to be quite a bit of words. So I might use a pencil so I can write a little smaller. So angle C and its images, because that's what we were creating, are equidistant. So there's that word again that we've been using a lot this module. Equidistant from the center of rotation, which is O. This is also true for angle A. Remember, we always capitalize angles and its images. And angle B and its images. Another way to say this is that corresponding angles corresponding vertices, that's what words they're using, lie on the same circle. You can think about definition of a circle. Definition of a circle meaning all points on the circle are equidistant from the center of the circle, whose center is the center of rotation. In this example, great. So determine the angle of rotation from one image to the next in the picture above. So remember, when we went from one image to the next, we're rotating an equal degree, an equal measure. So what is that measure? How many degrees are in a full circle? 360 degrees. And how many triangles did we make? Well, if we count them, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have to rotate 12 times to get back to our original. So if we take 360 degrees, one whole circle, and divide it by 12, the number of circles we made, we get 30 degrees. So we can say 30-degree rotation. And a direction is usually important, so we can just say, since we are going counterclockwise, we can say counterclockwise. Cool, let's keep going. So taking a look, the picture from the previous page was modified, so we only have some of the triangles. So taking a look here, they're only images that are increments of 90 degrees. And the pre-image, of course, is shown, and the center rotation is still O, even though it's not labeled anymore. So you'll notice it was modified and kind of shrunk, but my old picture doesn't work here. So you can reuse this piece if you wanted to by just using a different color on there. So like you could line up your origin, use the same origin, and you can just trace in a different color your triangle ABC. Just, being respectful of our resources, since we're probably not going to reuse this piece of wax paper again. So we can do that because I want you to learn as well as you can. I'm going to cut myself another piece just so you're not confused. Okay, so I'm going to trace my axis. I'm going to keep that as still as I can. And trace ABC. And sometimes making sure you can see those vertices can be really helpful later when you're doing your own rotations. So let's see. Verify using tracing paper that descriptions of the rotations are accurate. So notice if it's a 90-degree rotation, the reason we're working with 90 degrees is because in a coordinate plane, each quadrant is, dun, 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 90 degrees. So if I rotate so that this origin is lining up again with your X and Y axes, notice we are now lying exactly on the next image. So from my pre-image to my image, notice I'm going counterclockwise. Sorry, I'm going clockwise because I'm going from 1 to 2 and so on. So now I'm going to go, so that was 90 degrees clockwise, another 90 degrees, 90 plus 90 is 180 degrees clockwise, another 90, see how the origin, the axes line up really nicely, is 270 degrees clockwise, and then finally another 90 degrees is going to get me 360 degrees clockwise, and back where we started from. So I confirm. The rotation from figure 1 to figure 4 has been described as a 90-degree counterclockwise. How would you describe this rotation in the clockwise direction? So what they're telling me is that if I was going from figure 1 to figure 4, I can just go 90 degrees, and notice I'm going counterclockwise. But what if I want to go in the clockwise direction? I'd have to go 90, 180, 270. So this would be described as a 270-degree clockwise rotation. So now, just like we did before when we wanted to explore the slopes to see if we can find some type of pattern and prove if these are congruent, we are going to look at the rotation from just figure 1 to figure 2. We're just looking at figure 1 to figure 2. Remember, this is just a 90-degree rotation, and it's a 90-degree clockwise rotation. Rotation 90 degrees clockwise. Find the slopes of the following segments. So segment AB. So segment AB, I'm going to go up 2 and right 3, so that's 2/3. I'm going to stay on triangle ABC just because it's a little easier, a little more efficient for me. BC, I'm going down 2 and right 2, negative slope, -1. And then AC, we can tell that this is a horizontal line. Horizontal lines have a slope of 0. Cool. So that was our pre-image. And then moving on to our image that we're investigating right now, which is number 2, A prime, B prime, C prime. Notice it goes to A double prime, B double prime, C double prime, A triple prime, B triple prime, C triple prime. So taking a look here, A prime, B prime, I'm going down 1, 2, 3, and to the right 2. So that means this is a -3/2. Oh, do you see what I see? Okay, so let's take a look. B prime, C prime. It's a positive, it's going up. I'm going to go right 2, up 2, which reduces to +1. Okay. And then AC, AC is a vertical line. Do you remember what the slope of a vertical line is? That's right, undefined. Some number divided by 0. Where over here, this was 0 divided by a number. So what do you notice about these patterns? Do you see anything interesting? Well, what's the relation between corresponding segments in a 90-degree rotation? And this will hold true. Notice if we go 90 degrees clockwise or 90 degrees counterclockwise, B triple prime and C triple prime and C prime, B prime, these are they're extensions of the same segment. They have the same slope. And then B triple prime, A triple prime with A prime, B prime, they're parallel. And the same thing with A prime, C prime with A triple prime and C triple prime. So this holds true for a 90-degree rotation clockwise or a 90-degree rotation counterclockwise. So the corresponding segments that's what they're asking, between the corresponding segments are, well, if we look at the slopes, 2/3, -3/2. -1, 1. 0, undefined. What are those? Corresponding segments are perpendicular. -90-degree intersections. Because slopes are opposite reciprocals. So recall, we're just going to put a little note for ourselves. Translations slopes are equal. And in a reflection, slopes are opposite. So that's just a good note for us to remember, because if we're given two shapes, an image and a pre-image, and we're asked, hey, is this a rotation, reflection, or translation? We can identify that relationship by checking out the slopes of the corresponding segments. Awesome. Let's keep on keeping on. So what we want to do is we want to describe what happens in a 180-degree rotation of a figure, and what is the relationship of the corresponding segments. Well, if we go back to our diagram and we look at 180 degrees, remember that's two groups of 90, which means I can go counterclockwise or clockwise to get there. And here, AC with A double prime, C double prime, parallel, they're both horizontal. AB with A double prime, B double prime, parallel. And C double prime, B double prime with BC, parallel. So going back, what is the relationship of the corresponding segments? Parallel. If 180-degree rotation. And again, direction doesn't matter because clockwise and counterclockwise will be 180 degrees. You'll end up in the same spot. Okay, so we are going to examine segment PQ on the grid. Okay, look at it. Good job examining. Use slope to verify. Rotate segment PQ 90 degrees counterclockwise with the center of rotation at the origin and label the image. So what we're going to be doing is with our tracing paper, we are going to trace our origin, which is very important. I'm going to trace P. I'm going to trace Q. I'm going to take pencil and always double check what degree we're going. So we're going 90 degrees counterclockwise. So this is clockwise. So counterclockwise would be this way. Now I'm going to line this up perfectly. And I notice that Q is going to be at -2, 8. So I'm going to go -2, 8 and label that Q. And then notice I'm using a pencil because easy to make mistakes here. P is at -6, 2. Was it -6 or -7? Yep, -6, 2. Oops, and these are P prime and Q prime. Hopefully you noticed that. I'm going to use a straight edge tool to trace that line. And before I move on, I'm going to double check that if I'm lined up with what I think is my new image, can I rotate back 90 degrees and end up right on my pre-image? I can! Yay! Okay, so here we are, labeled center of rotation. I guess we can label this also. Label that O, center of rotation. Use slope to verify that your image is the 90-degree rotation. Remember, since this is a 90-degree rotation that we made, our corresponding segments, which there's only one here, should be perpendicular, opposite reciprocals. So if I take a look at segment PQ, my pre-image, I notice 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6. I'm going right and down, or up and left. So -4/6 reduces to -2/3. So then if I come over to my image and make a right triangle to find my slope, 1, 2, 3, 4, and then right and up, 1, 2, 3, 4, 5, 6. 6/4, which is 3/2. 3/2 and -2/3 are opposite reciprocals. So yes, -2/3 and +3/2 are opposite reciprocals. Hence, therefore, ergo, segment PQ and segment P'Q' are 90-degree rotations. Cool. Use the distance formula to verify that point P and corresponding point P' are equidistant from the center of rotation, which is the origin, which remember is 0, 0. Write the distance in simplest radical form. Awesome. So what we want to know is we want to know the distance between P and the origin and P' and the origin. So let's take a look at PO. So segment PO, segment or point P is 2, 6. And the origin O is 0, 0. So taking a look here, distance is going to be equal to the change in the x value squared plus the change in the y value squared. So it's pretty easy since we're using the origin. 2 minus nothing is 2, so 2 squared. 6 minus nothing is 6, so 6 squared. 2 squared is 4. 6 squared is 36. Order of operations, 36 plus 4 is 40. And we have to think, are there any perfect square factors that go into 40? Yes, there are. If you have 40, that's square root of 4 times square root of 10, and square root of 4 is square root of 2 and square root of 2. So we can pull out the 4, it becomes a 2, or pull out the 2 squared, it becomes a 2. And square root of 40 is 2 square root 10. So if we're doing this correctly, we should end up with the same answer for P'. There's no O' because the center of rotation just stays the center of rotation. So see P' O. So P' is -6 to, -6, 2. And the origin is 0, 0. So again, our distance is the change in x squared plus the change in y squared. So again, we're going to have -6 squared plus 2 squared. So we're going to have square root of 36 plus 4. A little bit of deja vu here, square root of 40. Is there any perfect square factors that go into 40? Yeah, it's 4. Woo! So we end up with 2 square root 10. So yes, indeed, P' to the origin and the origin to P are equidistant. And if we did the same math with the origin to Q and the origin to Q', switch those around, we'll end up with the equivalent distance. Not the same distance necessarily as P and P', but these will be equivalent. So what we're going to do is we're going to take a look at number 6, and we're going to be focusing on a 90-degree clockwise rotation. So if we take a look at our pre-image, quadrilateral EFGH, we're going to rotate this 90 degrees clockwise about the origin and label it E prime, F prime, G prime, H prime. So maybe we might need a new piece of paper. Maybe you can still reuse yours. Really impressive if you can. That's great. So I'm going to, again, trace my origin, or you're just using your same origin as before. I'm going to plot my coordinates for E, F, G, H, then trace. And this way it's just a little bit more obvious like where those actual coordinates line up. E, F, G, H. Sometimes going over it more than once helps it show up for you all a little better. Anything can do to make it better. I try. Okay, so again, we are going which way? Clockwise and 90 degrees. It's up nicely. So G prime is going to be at 1, 2. H prime is going to be at 1, 6. F prime is going to be at 1, 2, 3, 3. And again, just like when we were doing our reflections and translations, you could count H is up 1, right 2. So I can go up 1, right 2 to get to E prime. Make it nice and dark, especially when you're graphing along grid lines. Looks nice. Okay, so we rotated, and of course we'll double check our rotation. 90 degrees. Oh, it's almost perfect. Oh, yeah, it's beautiful. So nice. Way impressive. So we're going to complete the tables. I gave you the original coordinates. You're welcome. And what we want to know is the coordinates afterwards, and then think about a general rule. So why don't you pause me, because you've been really good at this in our last lesson, and take a whack at it. Okay, let's see how we did. So E prime, I ended up with 3, 7. F prime, 3, 3, like we said when we were graphing. G prime, 1, 2, and H prime, 1, 6. So taking a look here, examine the coordinate points and state a general rule. Well, X comma Y is going to be graphed to. Notice -7 was an X value, but now 7 is the Y value. -3 was the X value, and now 3 is the Y value. -2 was the X value, now 2 is the Y value. -6 was the X value, now 6 is the Y value. So how does the original X value compare to the new Y value? The new Y value is the opposite of the original X value. So here, this Y value is going to be the opposite of whatever this was. Okay, well now let's take a look at the, oops, dropped my marker. Let's take a look and see if we can figure out what the new X value is. Well, 3, the original Y value, the new X value is 3. 3, 3, 1, 1, 1, 1. So the original Y value is now our new X value. Remember, in the beginning, we defined these values as x and y, so we're going to keep those original values, but over here. Will the same rule for a 270-degree clockwise, counterclockwise rotation work? Okay, well, let's think about this. What we just looked at was a clockwise 90-degree rotation. And this rule will work for any clockwise 90-degree rotation in the entire world. And this is only true for 90 degrees clockwise. It has to be clockwise. Because obviously if we went counterclockwise 90 degrees, the coordinates aren't the same anymore. So they're asking us, what if we went counterclockwise 270 degrees? Well, how many multiples of 90 is that? So that's 90, 180, 270. Oh, by golly, it is. So yes. Make a better smiley face. 270-degree counterclockwise rotation results in the same image as a 90-degree clockwise rotation. Which is great, which means by coming up with this one rule, it applies to both rotations. Yay! Efficiency. Cool. So let's keep going. Little wax papers everywhere right now on my desk. So now we're going to look at another pre-image. And what we're going to do is we're going to rotate. And if I'm correct, this is the same. It's the same shape. Everything's labeled. So what's wonderful is we can just reuse that. I'm trying to get rid of that glare for you. Cool. So I'm going to reuse my same tracing paper. What we're going to do is we're going to rotate, and I always like to underline what I'm doing, 180 degrees clockwise. And I always like to think about a clock when I'm thinking about this. And about the origin, which is super important. And we're going to label it E prime, F prime, G prime, H prime. So I'm going to line this up. Perfect, perfect. And now I'm going to go 180 degrees clockwise. Remember, when you're going 180 degrees, direction doesn't matter. I don't know why I got closer because my headphone's like right here speaking into the microphone. I don't need to get closer if I'm whispering. Okay. Taking a looky-loo. So 2 groups of 90. End up in this quadrant here. It looks like it'll be about like that because I know they're going to be on coordinates. So I will have H prime, and then I'll just double check. Down 1, down 2, right 2. Sorry, down 2, right 1. Come on. 1, 2, 3, 4 over to get to G. 1, 2, 3, 4. Down 2, right 1 to get to F. And oops, all of those are primes because these are images. And I'm just going to freehand this real quick. Remember, try to make, if you're using a pencil, nice and dark so everyone can see. And then before I move on, I'm going to double check that if I rotate another 90, 180, I end up right on there. Notice mine's just slightly off, but that's okay. It's probably just my printer. It's almost perfect. Could have just been moving my origin around a little bit. Looks good. Okay, so we rotated this. We're going to complete our table of values. So taking a look here, we end up with E prime, which is 7, -3, F prime, 3, -3, G prime, 2, -1, and H prime, 6, -1. Cool. 6, perfect. So now we're going to look at the coordinate pairs and we're going to look for a general rule. So remember last time how our x's and y's kind of swapped around. So we want to be aware of that. That's an option that could be happening with us. So let's see. I'm going to look at my original x values. And I'm noticing that x value is actually staying corresponding with the new x value, but it's the opposite of what it was. -7 went to +7, -3 went to +3, -2 went to +2, and -6 went to +6. So it's the opposite. And if we look at the y values, they also go to the opposite of the original y values. Okay, so taking a look, and you can always double check that. Why is this happening? Well, it's actually because if we take a look at these, ooh, that marker's dead. If we take a look at these quadrants, remember it goes 1, 2, 3, and 4 for the quadrants. If I have an x comma y here, this is going to be a positive. Over here, we're going to end up with a negative positive for x comma y. Here, we're always going to end up with a negative. And here, we're going to end up with a positive negative if we're in this quadrant. So if you think about going 180 degrees, you're always going to be kind of going in the diagonal quadrant from each other. And notice the diagonal quadrant from each other is always going to have the opposite sign than what you came from. So that's why this happens, just in case you wondered. So if the figures rotate 180 degrees counterclockwise, are the coordinates of the rotation the same as coordinates for a 180 degree counterclockwise rotation? Yes. Halfway's halfway, y'all. 180 degrees is halfway around a circle in either direction. Hence, a 180 degree rotation clockwise or counterclockwise. I know, why is it such a long word? Results in the same image. Cool. Awesome. So now we've talked about a 90 degree rotation clockwise, a 270 degree rotation counterclockwise, a 180 degree rotation clockwise, a 180 degree rotation counterclockwise. So now I guess we just have to go, hey, 270 degrees clockwise. Let's do that. So rotate the pre-image E, F, G, H 270 degrees clockwise and label it E double prime, F double prime, G double prime, H double prime. So we're going back up here. I'm going to pick a different color that I didn't use already on this coordinate plane. So I'm going to make it purple. So I'm going to circle this in purple. So we're going 270 degrees clockwise. Lucky us, we can use our same awesome tracing. And what we're going to go is we're going to go 270 degrees clockwise, which you might, I'm doing the weird whispering close thing again, which you might realize is a same rotation of a different degree in a different direction. And I know there's only 2 directions you can go. Okay, so taking a look, we're going to 270 degrees clockwise. So clockwise like a clock. 12 to 1. So that's 90, 180, 270. Line them up. Really nice job. So G is going to be at -1, -2. Oops, I remember I'm using a different color now. So this is G double prime. Remember to label it such, G double prime. H is 1, 2, 3, 4 units down. 1, 2, 3, 4 units down. H double prime. E is left 2 down 1. E double prime. And 1, 2, 3, 4 units up. 1, 2, 3, 4. Oh, my labels didn't get in the way. That's really nice. F double prime. Connect to make your image. Oh, beautiful. Okay, so we have our original coordinates still, and we need to list out our coordinates after the rotation. So why don't you go ahead and fill in this table and see if you can come up with the rule this time. Go ahead, pause the video, and then double check in when you're ready. Cool, so taking a look, we have E double prime, F double prime, G double prime, and H double prime. And we ended up with, what's this? -3, -7, -3, -3, -1, -2, and -1, -6. Awesome. So you filled in your table. Examine the coordinate pairs, state the general rule. So our general rule, we're always going to go x, y. And let's examine our original x values and what happened to them. Oh, interesting. Our original x values are now our y values. Not taking the opposite, not doing anything to it. And then let's look at our original y values. Original y values. Now, if you take the opposite of them, turn into your x values. Dun, 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 dun. And will this rule work for a 9-degree counterclockwise rotation? Well, let's investigate. If I wanted to go 9 degrees counterclockwise, bloop, bloop, it's amazing. Okay, so yes. 90 degrees counterclockwise. The big long word, counterclockwise. And 270 degrees clockwise. Result in equivalent, ooh, fancy word, equivalent, sounds good, images. Just for my notes so I can find that easier. 9 degrees counterclockwise and 270 degrees clockwise. It might be helpful soon. Okay, keep on keeping on. So what we're going to look at is 90 degrees counterclockwise. So 90 degrees counterclockwise, and we're going to be working with triangle ABC. So maybe you think about what else this is equivalent to. So go ahead, maybe you can use the same piece of tracing paper. Maybe you need a new little slice. Almost done. Why don't you do number 8 and see if you can start to fill in the table for 9. Pause the video while you work on 8 and 9, and then we'll get started. Okay, let's see how we did. So taking a look, we always want to trace our origin because that's our center of rotation here. That's what they told us. And we're going to trace our vertices for ACB. And we are going to go 90 degrees counterclockwise. So remember, clockwise would be this way. So we want to go counterclockwise. Line them up real nice. B prime is going to be at 2, -1. And when you label your vertices, you know where the rest of your shape is going. So like, don't label your B like here, because it's not gonna make your shape look as pretty. A, 5, -3, and C prime. Maybe I'll grab a color. And of course, double check. Ta-da! Beautiful, beautiful. Okay, so I did that. And you looked at your coordinates, 9 degrees counterclockwise. So this is coordinates after 180 degrees. Let's just say 90 degrees counterclockwise. Sorry, must have just copied the table from the one before that. So you just circle that and be like, bloop, that's what you're doing. So we have A prime, B prime, C prime. Hopefully you didn't do the 180 degrees. So 5, -3, 2, -1, 2, -5. And you looked at investigating your rule. And maybe again, you start looking at your x values, your original x values, and you noticed, oh my goodness, and your y values. And you notice that xy was going to be mapped to -y x for a 90-degree rotation counterclockwise. This is a 90-degree rotation counterclockwise. And that's going to be important for you because now you had this awesome table to fill in. So if you haven't had a chance to fill in this table yet, I want you to pause. I want you to go back through your notes and see if you can fill in our awesome table with our rules. Okay, so 90-degree rotation. Remember that xy is going to go to y -x, which means -4, -9 is going to be what now? Now it's going to be -9, 4. Our 90-degree rotation clockwise is the same. It's the same as 180-degree rotation counterclockwise. Oh, sorry. Misspoke. A 90-degree rotation clockwise is the same as a 270-degree rotation counterclockwise. Okay, so I'm going to write that same rule here because they're the same. Might as well be efficient. So it's going to go to the same. -9, 4. Cool. Now, remember, then a 270-degree rotation clockwise is the same as a 90-degree rotation counterclockwise. So the rule for those two was xy went to -y x. xy goes to -y x. So now -4 was our x. So now it's our y. And -9 was our y, which means the opposite of it, +9, is our x. 9, -4, which means this one's also done. 9, -4. Cool, cool. Okay, 180-degree rotation. So 180-degree rotation, these are same, no matter the direction. So xy goes to, if you looked up in your notes, -x, -y. You can also think about how we're changing diagonally our quadrant. xy goes to -x, -y. So xy before was -4, -9. So now +4, +9. And our last, 360-degree rotation. Thank goodness. XY is mapped to XY. It's like so easy, you think you're doing it wrong. We go 360 degrees from -4, -9. We end up back at -4, -9. Woohoo! Okay, so let's take a look at these directions. Directions. Name the transformation, if it's a translation, reflection, and or rotation, that is described by the given statement. The slopes of corresponding segments may change. So which are the ones that the slopes may change? Remember, a translation, just that rigid motion of up, down, left, right. We can't change the slope. But in a reflection, we can change the slope, and in a rotation. Notice it's saying may change. Not for sure. I know there are some that will not change. Corresponding angles in the image and pre-image have the same measure. So remember, all of these motions are rigid motions. So I'm going to make a little bubble over here. Rigid motions include translations, rotations, and reflections. And that's really important because rigid motions create congruent figures. Make congruent, I guess we can call them images. Congruent images are the same size and same shape. So if we take a look, corresponding angles in the image and pre-image have the same measure. That's going to be all three. Translation, reflection, and rotation. Corresponding segments in the image and pre-image are the same length. Well, that's what it means to be a rigid motion. Rigid motion, translations, rotations, and reflections make congruent images. Congruent images have equal length sides and equal measure angles. So it's all three of them again, the trifecta. Translation, reflection, and rotation. Nice, excellent job. So the next part, if you're interested, is an extension on translations, reflections, and rotations. You're going to use a pencil and start with your pre-image, and then it says to use certain color pens. And I will post my solutions in the worked out, filled in lesson. So if you feel like you want to try this out, I will post my worked out and you can see how you do. Notice you're always, you're going to reflect this original quadrilateral and then you're going to rotate your reflected figure. So you're not always working back at your pre-image, you're working back from your previous image. So it's a pretty fun activity. And like I said, I will post my answers with the worked out solutions that are filled in. And I hope you enjoyed this lesson. You're doing a fabulous job. Keep up the great work. Do your best and be nice to everyone. Video bar out.